Good morning. Thank you for having me. I'm Massimo from the University of Zurich. The title of my talk is Neural Text Normalization with Adapted Decoding and Buffer Speech Features, and we do text normalization on Swiss German WhatsApp messages. Here you can see my co-authors. I guess you can see this as a sequel of the work that we presented last year here at SwissText, so let's delve into it. What is text normalization? Well, it's the task of converting non-standard text into a standardized form, which is suitable for NLP tasks and NLP tools and applications. When do we have non-standard text? Well, we have some examples. We have historical texts, dialects and languages with no orthographic standard, and computer-mediated communication. When we talk about WhatsApp messages written in Swiss German, we have two of these elements combined. Because Swiss German is a dialect, and there are no spelling rules, and WhatsApp messages are an instance of computer-mediated communication. So we have two factors that contribute to the variation of the source text. We have a lot of variation in the source text. The first factor is the dialect factor. So Swiss German is a dialect, there's a lot of regional variation, and there's no orthographic standard, so the same word may appear in many different spelling variants. And this is just an example from the corpus that we've used for our experiments. The same word with 8 different spelling variants and the corresponding frequency, and they can all be mapped to the same normalized form, which represents them all. The second factor is the CMC factor. So CMC is something between written and spoken, and it has some peculiarities. Here just a list of them, just some examples. We have emojis, emoticons, vowel reduplication, unconventional abbreviations, typos, and unconventional casing. So, normalization is important due to the high degree of variation that we have. And so this is just an overview of the methods that we use. We approach text normalization as a machine translation problem, and we start with a plain character-level neural architecture, an encoder-decoder model. We call it NMT, so neural machine translation. And then we propose 2 enhancements. Enhancement number 1 is what we presented last year. It's an integrated word language model. We call it NMT plus LM. Enhancement number 2, we use linguistic features, and more specifically part-of-speech features as input. And we do that because we want to solve some cases of ambiguity. This is an overview of the corpora that we have used for our experiments. We have 2 corpora. One main corpus, which is a corpus of WhatsApp messages written in Swiss German and manually normalized. It consists of 54,000 alignment units, and I will explain later what we mean by alignment units. We have a second corpus of SMS messages. This is larger, but we use only the target side of this corpus to train some additional integrated language models, and we'll also elaborate a bit more later on this. So this is how our corpus looks like. We have the source side with Swiss German and the target side with the normalized forms. As you can see, most alignment units are 1-to-1. So one Swiss German word and the corresponding normalized form. There are some cases of 1-to-many alignments, like here. Similar thing here, this is due to the tendency that Swiss German has to merge words together. We also have some rare cases of many-to-many alignments and many-to-one alignments. So since our second approach requires part-of-speech tags, then we need to tag our corpus with part-of-speech tags. And how do we go about doing this? So we decided to tag the normalized part of the corpus. And for this we use the tree tagger. We train the tree tagger on the SMS corpus that I've mentioned before. And we tag the target side of the WhatsApp corpus, and so we obtain a silver standard. This is what we will use later to assess the performance of our tagger. It's not a gold standard, it's not manually annotated, it's automatically annotated, but still maybe it can provide a good indication of the performance of our tagger. Then we take advantage of the fact that we have this nice alignment, and we do a projection of the part-of-speech tags onto the source side. So we just copy the part-of-speech tags. And then we split the corpus in train set, development, and test set. So 80%, 10%, 10%. And we train the B tagger on the train set of the corpus. Why the B tagger and not the tree tagger? Well, we tried both and we saw that for this particular task, the B tagger performs better. So we trained on the train set and then we applied to the dev and to the test set. And now we have annotated Swiss German. And we can compare it with the secret standard that we had in the first place. And we see maybe there are some errors. Maybe this should be an adverb and it's being tagged as an adjective. Again, we have this accuracy, which is roughly 90% for the dev and the test set. It's a proxy because it's the reference is a silver standard, but still a good indication of the performance of the tagger. And this is an overview of the methods, of the baseline, because we computed the baseline and we do as follows. For each Swiss-German word in the test set, we select its most common normalization in the training set. And this results in 3 categories of words. We have unique words, which are always normalized the same way in the training set. We have ambiguous words, which have more than one normalization form. And here we select the most common one. In case of tie, the choice is random. And finally, we have new words, words that have not been seen during training, and they're just copied from the source to target. And this very simple method produces an accuracy of 83.72%, which is a very good baseline. As you can see, the performance on unique words is hard to beat. Where we want to see an improvement is here on ambiguous words and new words. We have a second baseline for the scenario in which we use the part-of-speech tags. And for this baseline, unique and new words are exactly the same as the previous table, so the figures are the same. What changes is ambiguous words, because here we have 2 subcategories. We have post-unambiguous, in which one source word has 2 normalization forms, but for each form we have 1 part-of-speech tag. And so we select the normalization form that has the same post tag as the source. Then we have the post-ambiguous subcategory, and here we have cases in which one source word has 2 or more normalization forms, and they all have the same part-of-speech tag. So in this case, we select the most common normalization in the training set. And the accuracy here is 85.64%. So this is an illustration of the plain framework that we start with. We use an encoder-decoder model with STM, so bidirectional encoder, and self-attention mechanism. And maybe if you're interested in the details, we can talk about it during the discussion, but as you can see, this is a pretty standard architecture, so nothing really fancy here. Just notice that we operate at the character level, so each input unit is a character. And this is the first enhancement that we introduced last year, but just as a refresher, we use an integrated language model at the word level. And we apply this language model with a synchronization mechanism that was introduced by Lusetti and Summarization on the task of morphological segmentation, and here we use it on this task of text normalization. So the idea here is that maybe the plain NMT framework produces an output which is a plausible sequence of characters, but it's not a word, at least according to the training set. It's a word that doesn't exist, because the NMT system has no notion of what the word is. So it would be great to have this integrated word-level language model that is aware of what the word is and can contribute to the loss function and say, well, this sequence that you produced as an output makes sense in terms of characters, but it's not a word. So maybe the probability is not so high. And so what we do is that at the decoding time, hypotheses are generated at the character level, and then we have 2 scores, one score produced by the plain NMT model at the character level, and the other one is the score produced by the integrated language model. The 2 scores are combined when we reach a word boundary. word boundary can be the end of the sequence or can be the white space between two words. And the two scores are combined with a weighted sum, and we optimize the weights with MERT on a development set. This is the second idea, the second enhancement. Use part-of-speech features as input to solve some cases of ambiguity, and it's the very same architecture that we've seen with the plain NMT model. So as you can see, there's our encoder here, bidirectional encoder. This is a soft attention mechanism. And our decoder, the only difference is that each output unit is now a function not only of the current hidden state of the decoder and the context vector, but also of this vector, which is a pos embedding. So it's the vector representation of the part-of-speech tag. And when we have a sequence of two or more part-of-speech tags, then we take the average, and there we have our vector. So, results. We have highlighted in green the results of this last method, so with that, the new method that we propose. But just to allow a comparison, we also have the results of the previous methods. We started with the baseline, the first row that I've introduced before, 83.72%. And we also compared it with statistical machine translation. So character level statistical machine translation is still, in many aspects, the state of the art in text normalization. And when we used the plain neural architecture here, we already have an improvement over CSNT. Though I have to say here, we use an ensemble of 5 models. And then when we add the integrated language model trained on the WhatsApp corpus and on the SMS corpus concatenated, then we see that the accuracy is now 87.09%. When we use the part-of-speech tags as input features, we have our baseline that we also saw before. Only the plain neural architecture with the part-of-speech tags produces already a substantial improvement, 89.13%. But when we use the two enhancements combined together, so the part-of-speech tags and the integrated word-level language model, then we see that the performance is 89.53%, which is the best performing model. So some error analysis. Here we have cases in which the integrated word-level language model improves the output. So we have the column here with the source word, it's just German. This is the wrong prediction made by the plain NMT model, and this is the correct prediction made by NMT plus LM, which is the same as the gold standard. So we have 3 groups, A, B, and C, 3 categories. Group A is when the normalized form is just 1 word. Group B is when the normalized form is 2 or more words. And group C is when the normalized form was not seen in the training set of the WhatsApp corpus, but it was seen in the SMS corpus. So this is a good indication that having more data to train our additional language models can reduce the number of unseen words. And now the error analysis on the second enhancement, part-of-speech features. We have also here the Swiss German words, the wrong prediction made by NMT plus language model, and the correct predictions made by the NMT when we use the part-of-speech tags. The test set is about 5,000 instances, and here we have the number of occurrences of each of these phenomena. For example, if you look at the first row, you have the source word be, which can be normalized as been, and this is a verb, or as by, and this is a preposition. Of course, if you don't have the part-of-speech tag, the model can only, I don't know, guess, maybe. But if you know that be in the source text is a preposition, because your part-of-speech tagger did a good job, then the model with part-of-speech features has no problem predicting the correct output. And all these cases are similar. So, to conclude, we have 2 approaches that we have implemented, and we have shown that they are complementary, and together they work really well, and they produce an improvement of the neural models, of the plain neural network. So the first enhancement, the integrated word-level language model, helps to improve performance by introducing word awareness in the character level framework. So not only, the sequence must be correct in terms of sequence of characters, but it must also be a word that makes sense according to the training set. And then performance is improved also on unseen input words, and this is achieved by using additional language models. So you can extend your language model and reduce the number of the unseen words. Secondly, to our second approach, we use part-of-speech tag information, and this helps to improve performance on ambiguous words, that is, words with different possible normalization forms. And future word, it would be interesting to use our method for the normalization of other languages, characterized by dialect variation. We believe that the two devices that we have created are portable and they can be used successfully on other languages. It can also be a good idea to increase the amount of target data, so more language models on which you can train more data on which you can train your language models and to address unseen words, and then finally tackle the problem of ambiguity. Also here it would be good to have a more fine-grained text set. There are some examples. If you have adjective as a part-of-speech tag, this doesn't really distinguish between, nominative or accusative, and so, or maybe one more example, if you have the Swiss-German word mir, this can be normalized as mir or as wir, and they are both personal pronouns. So you don't have much information really to disambiguate. A more fine-grained tag set would be useful here. And then it would be also interesting to use context information more directly by using longer segments. Here we normalize just each word in isolation, and maybe if we use longer sequences, segments, or even sentences, this could be a good idea maybe to get some context and solve even more cases of ambiguity. That's it. Thank you for your attention.
Very much for being in time. Any questions to Massimo?
I named it. Oh.
You mentioned that you have different slices in your data. So these are the ones that are not ambiguous, the ones that are ambiguous, and so forth. Did you analyze which part of the data your method improves with language models and the part-of-speech features?
Yes. So,
for example, it'd be interesting to know whether the unseen stuff actually gets solved by this.
Yes. So we have a very thorough error analysis that, of course, the table that I show here is just a summary. This baseline, if we look at the two categories here, part-of-speech and ambiguous. One example is, so when you have one normalization form and so one source word and two normalization forms, and they have two different part-of-speech tags, and this would be the case of B, because B is by or bin, but the part-of-speech tag is not ambiguous. And in the other cases, the one that I mentioned before, the mir, that can be mir or vir, and in this case we have an ambiguity also of the part-of-speech tag. And so this is the baseline, which is just memory-based. Right now I couldn't tell you exactly all the figures about the error analysis. We have some more some thorough error analysis. There's also a paper that is going to describe this project in detail, and maybe if you contact me I can give you more details about this.
Thank you.
I have another question regarding the data sets that you used. I think if I remember correctly, it was about 30,000 paired sentences, right, or messages. How much was that?
So the corpus that we use, the WhatsApp the corpus of WhatsApp messages, well, this is a huge corpus in the 4 national languages of Switzerland. We use only the Swiss German messages, and only a portion of them has been manually normalized. And it's, about 5,000 messages, 54,000 alignment units, and we've seen that alignment units are normally just one word and the corresponding normalized form.
Oh, I see. Okay, so that means like you basically have 300,000 paired words, so to speak.
300,000
from the alignment units.
In the SMS corpus, yes, this is the number of alignment units, and it's usually the alignment unit is 1-to-1, so one word. So yeah.
Very actually insane. I mean, I remember I once read a paper, I think it was from Google Grade. They did also do a supervision translation for French English. I mean, they're usually the data sets are like much larger. Very actually surprised that it worked. I mean, it seems to work quite well for this number.
Yeah, so the thing that's a big problem about text normalization, that we have very little data to train our models, and that's why CSNT is the state of the art, because neural networks, they struggle a lot when they don't have a huge amount of data, and that's why also we try to come up with some enhancements to improve the plain NMT system, because we have to face the fact that we don't have enough data. Of course, it would be desirable to have more data, more annotated data. It's not always easy. The good thing maybe about this is that instead of having more data, which is expensive and time consuming, well, you can do it once for Swiss German, but then if you have to normalize another language, you have to start from scratch. But now here you have a device that is portable and that can work with little data, and so this is, I think, a very good advantage. Yes.
I was wondering if you have a measurement, again, question going in the same direction, if like twice as many data will make your advantage disappear. So you're getting advantage now with the limited amount of data that you have, and if you double the amount of data, then the part-of-speech information would not help anymore. Is that your estimate, or when will it disappear?
Good question. It's hard now for me to make an estimate, but maybe the same argument applies, that you can have more data, and if you're lucky enough to, but then this is like an ad hoc solution that you can work for Swiss German, but I think that our main idea was to create a device that we are sure that it has an improvement, and that maybe can be portable and can work in scenarios in which we don't have enough data. Maybe double the amount of data could be really good to do away with all the enhancements, and still even Moses could do a good job. And as a matter of fact, CSNT is still the state of the art in text normalization. So yeah, but always we have always had the same problem, that getting more data is not so easy. So.
Okay, last question. There was a question over here. No? Have you tried to use post tag of the previous and following words?
No. That's an idea that we are thinking about, to increase the context and then use additional features. So basically we have two encoders instead of only one. One encoder is exactly the same that we've described here, and the other encoder can encode the whole sequence, and then you get basically the embedding of a word, because this encoder would operate at the word level in context.
Yes.
And then you have this feature, or you can even have not only the words, but also the part-of-speech tags of the neighboring words, and that would be certainly a good idea, and that would be probably the next step. So maybe, it's not a trilogy, it's going to be a tetralogy, and maybe next year we're going to hear again to show you this
Actually, I
sequel.
as one of the authors, we have done something that Massimo was not up to date, so there is a new piece of work on my web to archive, so it's not published, but it's there. So we have tried these things and it helps.
Okay.
But it's so powerful that it has to be locked up for the good of humanity.
Okay, thank you very much.
Thank you.